Well, firstly, welcome everyone. Thank you for attending today. It's already been mentioned, but I am Luke Carwardine, and today I will be discussing challenges developing an Android-based system for two-wheel vehicles. It's a bit of a long title. I probably should have shortened it. So firstly, a bit about me. I'm an engineering manager at Drive Mode, and I manage a team that works on the IVI, which is an in-vehicle infotainment system, and that's the screen you see here mounted on the bike. You can also see here we have a companion app as well. A companion app is done by a separate team, but it is an integral part of our ecosystem and works directly with the bike. A bit about Drive Mode itself. We're a company which is trying to deliver smarter, safer and connected driving on any vehicle. So today I am focusing on just two-wheel vehicles, so motorbikes and scooters, but we do four-wheel stuff as well. And I should note we were acquired by Honda in 2019, so about 6 years ago. So the software you're going to see today runs on or targets Honda vehicles. So IVI, two-wheel Android, how does all this fit together? The easiest way for me to show you this is a quick little video here. Little ad from Honda. Apologies if you don't like ads. So here we have our bike that's on the market, the CUVe. It's an electric bike, has swappable batteries. You can see here we support navigation and a map system. Cool little through screenshot of our dashboard. What else? This bike was, here we go. When the rider changes riding mode, we switch themes. We need to do full screen overlays, showing reverse in this example. So this bike was released into the market at the end of last year into India and Indonesia, and this year it was made available in Vietnam, various European countries, and even here in Japan. So I guess if you want to see more, go to your local Honda dealership. Cool. So hopefully you have an idea of, the product and what we're trying to deliver to the market now. So let's focus on the IVI software itself. What are we trying to achieve? So firstly, we want a unified system. Everything needs to work together seamlessly. We don't want to feel like a collection of applications. Secondly, we want a modern experience. Quite often when I talk to people about automotive software, they talk about how it feels slow, it feels clunky. The UI might have a feeling that it was designed 10 or maybe even 20 years ago. We don't want that. We want to be a modern experience that not only feels like it was designed today, but it feels like it's still going to be the future. And then lastly, and perhaps most importantly, we need to ensure that our riders stay safe. My lead designer gave me the term glanceable composition. I had not heard this term until about a week ago when I was putting these slides together. But this basically means that our UI is composed in a way where you only need to briefly look at it to understand what's going on. This means, using icons instead of text, using colors to indicate various modes, and where we do need to use text, it needs to be clear and concise. This way, the rider can maintain focus on the road instead of looking at the screen. So, what about Android Automotive OS? I've been hearing this all through the conference so far to people I've talked to, and it's the obvious thing. For those that don't know, Android Automotive OS is different from Android Auto. Android Auto is like Apple's CarPlay. Android Automotive OS is the Android operating system built for supporting vehicles or cars typically. So let's have a look at what is in offer for Android OS. So the default UI is tailored towards cars. It still has a launcher, it still has a system UI, but it's modified for being a screen in the car. And the second thing is it offers this car service. And this is like a standard Android system service you'd be used to using in mobile development. But it offers managers that deal with the car. So for example, if we want to get the speed of the vehicle, that comes from the car property manager. We can listen to power states. There's a car audio manager too. There's a separate Bluetooth manager. But as the name suggests, it's not even vehicle service, it's car services. So we found that, this isn't really tailored to our use case. On top of this, I feel Android Automotive OS, it launched in a bit of an undercooked state. It was missing things that I think it should have had. When it launched publicly with Android 10, it already had deprecated features. This is because Google had been working with automotive manufacturers with it on Android 9, but they weren't made public at the time. But the thing is, automotive manufacturers had already been trying to put Android in cars. So before Google was supporting this, manufacturers had to come up with their own interfaces. So we aren't even guaranteed that the values we need are going to come from any of Google's car services. So we have custom interfaces that we need to deal with as well. And yeah, really, it doesn't matter what is at the service level or the system level in this case. We need to be able to support it. In fact, we have a case where the Android framework itself has been modified. So we need to support different devices with non-standard Android frameworks. And lastly, and perhaps most importantly in regards to the OS itself, we're not just trying to be another app. It's not, you don't download the Drive Mode app onto your Android system and click it from the launcher and open it. We are the system. And we're the whole user experience, really. So we have no need for the car launcher or the system UI in our case. So as you can see, we need to decouple, not really from the vehicle itself, but the interfaces to the vehicle. And to do this, we needed to start with a mindset of this being able to run anywhere. As I said, we need to be able to run on any sort of interface. Why not phones and tablets? Raspberry Pis are cool because you can get little Pi hats that talk to CAN. You can connect them up to vehicles, so you can do customizations there. And even in the emulator, if a developer can use the emulator, it's much more easier to develop. So ultimately, we actually don't even need Android Automotive OS. We just need a system that runs Android 10 in our case. But to achieve this, we don't want to make it excessively complex. So we want to use a standard modular architecture, something that our developers are familiar with and know what they're going to be running into, I guess, at the system level. And in these modules, we have a very simple rule. Either the module must be common, so have no vehicle dependencies, or it must only target a single vehicle, because if we start targeting multiple vehicles, we get conflicting APIs and all that type of stuff. So we need the separation down at the module level. So how do we achieve this? It all starts at the bottom with the build system. So we have a lot of complex requirements. We actually need to deploy multiple applications. We are not just a single application on the bike. We are an ecosystem of applications. Some of these applications are for production, some are for debug only, and in fact, in our case, we are actually able to debug remotely from a desktop application, and that's integrated into our build system as well. To achieve this, we have a custom grade or plugin architecture. And I guess this is primarily focused on trying to reduce the amount of boilerplate we need for common configurations and make things easier for the developer. For anyone who has ever worked with the AOSP, you will know it is a big and heavy beast to deal with. It takes a very long time to compile it. So one of the things we've also tried to achieve is having the application be separate from the AOSP, not integrated into it directly, and our Gradle system offers tasks and support to inject during the AOSP build time. So we don't need to directly have it. So this actually includes stuff like generating the Android.mk files as they're needed. And we've invested all this time up front in the build system to reduce developer costs and ultimately the developer's stress later during the development cycle. So I also want to talk about build variants. We're not doing anything super special here. Anyone who's used these before will be reasonably familiar with what we're doing. But we do have an extra dimension. Most people have probably only worked with 2 values. We have 3 in our case. So the first one's the environment. What backend are we talking to? In our case, we have staging, which is a development one. We have a UAT, which is more of a QA-focused one. And we have production, the real environment. Next up, the vehicle. What hardware is it running on? This is obviously the most important one. This could expand quite far. My example here is very simplified. I haven't given away all our secrets, but we can have a bike and a scooter in my example here. And this is the important one because as you can see at the top of this diagram, this dictates what modules get introduced into the build. And this is how we separate out conflicting libraries and APIs and other requirements at that level. Lastly, we have a build type, develop or release. You might be questioning, why does that say develop instead of debug? So a bit of trivia. When you're dealing with the AOSP has 3 build targets: engineering, user debug, and user. And early on, we were discovering that when you combine an AOSP build type with our build type, people would occasionally say, well, I've got a user debug build. And we didn't know, did that mean it was an AOSP user debug, or was it an AOSP user with a debug version of our software? So we made the decision to rename the debug target within the Android Gradle plugin system to be develop instead, just to reduce confusion. Next, I want to look at our Gradle build scripts. As I mentioned before, our plugin architecture is designed to minimize boilerplate, so lots of what you might normally see isn't actually here. This includes dependencies and configuration for common things like coroutines, flows, Jetpack Compose, and testing utilities. Up the top here is where we declare our plugin. And the main body here is the configuration that our plugin utilizes. At the top of the block, we have some common properties for apps, nothing too exciting here. More interestingly are these config blocks. So these allow for vehicle-specific configurations. And our example here is showing that for the bike, we actually want it as part of the AOSP, but for a scooter, we're not going to include it in an AOSP build. And this line here is specifically for the AOSP. So this generates the package override in the Android.mk file. And this is saying that our main app is going to replace the car launcher in the AOSP build. Lastly, we have this little custom dependencies block down the bottom here. This is currently used for automating license bundling at build time. So we can just include extra dependencies here, and all the license bundling just happens behind the scenes. We don't need to add anything there. And on a different script, I just want to quickly show how simple a script can be in our system. So here we have a library, and it's for design. And this is it. This is the entire script for the module. We don't need any other declarations. So, time to start coding, right? We've got a build system in place, all good to go. Well, first thing is you're going to turn on the bike, and there's going to be this screen somewhere on it. In this case here, it's in the top left corner, but this could be anywhere on the screen. And this is called the legal meter. And as the name suggests, it renders the legally required information. So speed and odometer are the big two here, but there are a few others. And this must be displayed when the vehicle is turned on, like almost immediately. We can't wait for Android to boot up. This just has to be there. So how does this happen? Well, it actually runs on a separate CPU. At Drive Mode, we are not responsible for this, so this is part of the hardware architecture. And it is always layered on top of the Android UI. As I said, it is legally required. We can never hide it or anything like that. And yeah, it could differ by vehicle. It could contain transparencies or animations as well. And the image is on the right here. The pink part is all the transparency. It's just easier to show it in pink up here. So that would be rendered on one CPU. It's probably a system running Linux or something like that. And down the bottom is our screen rendering Android. But this doesn't just impact the UI layout, it needs to be synchronized with the system. For example, matching the theme or perhaps the distance units. You can see in the top I've got kilometers and down the bottom I've switched it to miles. To add to the challenge, vehicle communication to the legal meter differs per vehicle as well. So sometimes we need to be reactive to the legal meter. Other times we need to be constantly telling the legal meter what state it should be in. And also one of the big challenges we've had is timings, particularly for the theme. So like when switching between light and dark theme, you've got to try and line them up so it doesn't look like they're out of sync. That is a lot more challenging than you would think. So I've already introduced one of the additional complexities we need to deal with. What else do we need to consider? Well, how do you interact with the software on the bike? And our inputs are primarily through buttons or joystick. When I say joystick, it's just a basic directional joystick, not a full analog thing. Now, there may be a touch screen still, or there may not. In our case, the vehicle I'm discussing today does not have a touch screen. But even if we do have a touch screen, it's difficult to interact with the touch screen when you've got your riding gloves on. In fact, it might be impossible if they're not capacitive. It also requires looking at the screen. I've already touched on rider safety before there. And we actually have a requirement that when the vehicle is in motion, the touch sensitivity of screens gets disabled anyway. So in motion, you can't use the screen. So for the button inputs, we only have a few of these available. Mainly the directions, up, down, left, right, and clicking in the center is a select. There are two buttons at the side here. They are mostly dedicated to app switching, so going from like the dashboard to navigation to calls to music to settings and so forth. But our architecture does support overriding these, and I'll talk about that a bit more later. And these limitations mean we need to think about how we really need to simplify our interaction model. And I'll talk about that a bit more in a moment too. So firstly, how do we actually handle all these key inputs? They could come from a number of sources. The composer's on-key event modifier, activity on-key down. The Android car service has a car input manager that also handles special keys. And it could have debug inputs too. In fact, we exploit some of the real estate under the legal meter for a little debug keypad. And if you're wondering how we interact with that without a touch screen, well, we do it remotely via screen capturing software, but it's very handy for the developers. So we've identified that the system, needs to potentially merge multiple inputs. But how are these inputs defined, and particularly from a design standpoint? Well, in our case, we don't just want basic up, down, left, right actions. We actually want long presses as well. So for example, when music's playing, you can see volume there with up and down at the moment. Holding it in center does toggle play pause. I guess this doesn't have it, but if you hold left and right, it will switch tracks as well. There it is. Excellent. So these are available at the global level. That is, they can be performed regardless of where we are in the application. And long presses aren't natively supported by Compose at least. Maybe other areas of Android do support that. So we need a custom mapping to support this behavior. So we finally arrive at our first piece of code here. And as you can see, we are defining the types of key presses we want to deal with. We have one for start. This just says an interaction has begun. Short release tells us that the user sort of, just tapped the button and it released. So that would be an action up in your native key events. And the more interesting ones, I guess, here are the long hold and long release. Long hold tells us, okay, now they're holding it down. Let's do an interaction with that. And long release just, says we're done. So we've got multiple sources and a custom key press type definition. How does all this come together? Well, as you can see in this diagram, all the inputs come into a centralized place and they get transformed. So stepping through this, at the top, we intercept, the native raw key inputs. So in Compose, right at the top of the composition tree, we have, an on-key event, and we are stealing the key at that point. And it's important that this key does not propagate down through the system. We capture it and then we block it. Nothing else in the application knows that this key press has occurred. The key press is then sent to our key press processor, as I've called it here, and this has the business logic inside to decide, has it started, is it a short release, is it a long hold, or is it a long release? And lastly, we emit these via flows to various observers. In our case, I believe we only have a single observer. I'll also talk about that a bit more. But you're probably wondering at this point, how does this interact with the UI? I just said that we're blocking all the keys. We're intercepting them and they're not going through the Compose tree or anything like that. But before I reveal how we do this, I need to switch topic to focus for a moment. So our UI philosophy is built around the concept of minimal focus. Many screens don't require any sort of focus indicator, and key presses have a direct action. So the top image here on this screen, up and down would change the volume, left and right would change the track, and center press would play and pause, just like the global overlay was doing. And we don't need focus. We probably just light up the icons in this case. But there are cases where we do need focus, and primarily those are lists. And the bottom case, as you can see, we've got a list there, we've got a little focus indicator around it, but the focus only works on a single axis, so it's fairly straightforward. However, there's always an however, isn't there? We need to support a keyboard, and this breaks all our rules. This is kind of my bane. It has a multi-axis up, down, left, right pattern, and it needs keys like the spacebar, which are really long, so it isn't even a nice, even grid. So initially, we actually had focus. We had the focus all being handled inside Compose. But this actually didn't work out very well. Compose just, for whatever reason, was not playing nice with us. Sometimes it would incorrectly focus on the wrong thing. We had occasions where it wouldn't focus on anything, and even sending key inputs would not change that. That was a bit scary. And this led to many, many hours of debugging. So we ultimately made the decision that we were going to handle the focus instead of letting Compose do it. So to handle this, we introduced this concept of focusables. Now, focusables are either a group, either a row or a column, or they're an item on the screen. For From the user's perspective, only the items actually hold visible focus, but internally the groups need focus to help manage things under the hood. We have a unit item, which is a special case for screens with a single focuser ball. This is a very rare case, but sometimes it makes sense to do this, so we have that there to simplify the implementation. And yeah, this is just a data model describing the layout and the view data. So this isn't rendering anything yet, and it's not managing the focus state yet. So the focus groups are used to build the layout. I must note this is not a unique concept. In fact, this probably feels quite familiar if you've ever nested columns and rows in Compose. And to make things easier for our developers, we have a DSL style API as well. As you can see to the right, we've got a code example at the top, and at the bottom is a visual representation of what that would generate. You may have noticed on the previous slide that there was a value for weight. We do support that. I don't have the example here though, but you'd use the weighting to make a large space bar on the screen. So now that we've defined a system for how focusable items are laid out, the next step is actually managing the focus state. And to do this, we have the aptly named focus group state. So this doesn't manage just what is currently focused. It manages interactions like, if a key press is pushed, what is the next object within the focus group that becomes focused? And it also helps us trigger side effects. Like if you do a select, we have a nice little animation to show it is being selected. Or if you're on say a vertical list and you push right, it might bounce the box or something like that. And that's all handled through this as well. Again, this isn't really a new concept. This would be similar to using something like text field state in Compose. So lastly, we've got our layout, we've got our state management. So we need to render the items to the screen. To make things easier, we have 3 composables that can handle this. One dedicated to columns and one dedicated to rows. And then we have a more generic one, focusable group, that handles more complex layouts. However, our only case of that at the moment is the keyboard that I've mentioned before. One very important thing I'd like to note here is you'll notice that there is still an on-click event here. And Compose is actually still responsible for the touchscreen events. We're only handling the key inputs elsewhere. So they still come through Compose. In my example here, I'm calling the focusable state select directly. In reality, we use an MVI architecture, and this would create an intent that then goes in through the view model, and that handles all of this, but I have simplified it here today. So, about those key inputs, I haven't forgotten. Now it's time to talk about how this all fits together. So, if you look at the diagram here, we can see the flow of keys from a raw input through to view models at the other end. So it comes down from the input. The key processor I was talking about before, we actually call key press emitter, and they come into this key redirector store. And each of these view models and the global overlay and everything here, they actually extend what we call a key redirector interface, and these register themselves with the key redirector store. And then it's the responsibility of our key redirector store to make sure that these get emitted to the right screen at the right time. So at the bottom here, as I mentioned, we've got our view models, and the priority of these is actually handled via our UI navigation state. It's a little more complex than I'm showing here, but basically our key redirector store listens to what is currently being navigated to and adjusts the flow as appropriate. So as you've got more screens on the stack with more view models, we can always make sure it is the view model for the screen that is currently focused receiving the keys. Moving up, I've already mentioned like the global overlay. We've seen the media keys in action. It is at a higher priority, and that is how it is able to react to all the long presses and not have those sent down through to our view models. Lastly, however, in some instances, we actually want those long presses to go to our screens. In fact, the menu keys that I showed earlier as well, sometimes we want to intercept those. And one example of this is we have a screen which allows the user to freely navigate around the map. So if they long press the joystick, it will move across the map freely. We don't have the global overlay popping over it. And the menu up, down buttons on that screen zoom in and zoom out. Finally, let's actually look at what's happening in the view model. So the key presses are coming to them, and this is showing how we handle them. To simplify things for our developers, we actually use a custom view model in-house, MVI view model. And this has a nice little interface called handle key press, which just needs to be implemented. So the keys come in here, and they can either be redirected to our focus group state, or in cases where maybe it has a direct interaction, they might get sent elsewhere. And once again, in reality, this is simplified. The way we typically do this will also generate an intent. That way it's matching the one that comes in from an on-click, and that intent is sent and handled in a common place. So yeah, reducing the chances of bugs. So I've only sort of touched the surface of what we work on here at Drive Mode, and unfortunately there isn't enough time today to talk about everything I'd want to, but I can mention a few more things. Now, these aren't all directly Android related, but well, they're still interesting. The first one, and a big pain point for us actually, is Bluetooth. We require non-standard behaviors from Bluetooth. That's been a lot of fun. And iOS and Android can behave differently. That is also a constant cause of problems for us. Moving on, OTAs in production. Generally speaking, the only way you can update a vehicle is via an OTA. You can't plug anything in. Even the dealer can't plug anything in. It might need to go back to the factory if you needed to update it. So it needs to be robust. And for Android itself, we utilize Android's update engine, the exact same engine, your phone and everything else uses. But as I mentioned before, we have other systems in the vehicle, the legal meter, there's other CPUs inside. Sometimes they need firmware updates too. So we need to handle all of that. Next is power management. Power management adds an interesting, state to the life cycle. And that's when the ignition, primarily turns off. There's probably an ignition on event too, but I don't know if we ever really use that. But ignition off is important because, we're not actually guaranteed that the system is suspending. The system might actually be having its power cut. So when ignition off comes, we need to ensure that everything in memory that we want to restore when the bike gets turned on later, has been saved out to disk. As you saw earlier in the little video, we support a map and navigation. Some of the challenges there are dead reckoning and map matching. These are related to, if the GPS signal is lost, perhaps we're in a tunnel or something like that, how do we accurately show where the bike still is on the road? And another challenge is selecting the correct road. Here in Tokyo, there's lots of highways above local roads down beneath. How do you know if you're riding down at the ground or you're up on a highway? So that's an interesting challenge. The UI overlay I've touched on multiple times already, but that has some interesting challenges. And lastly, almost all of our UI is custom components. This is primarily because we need to make sure they work safely. We've got some interesting complexities there. And it ensures that our developers are always using safe, components that match the safety regulations. So the developer doesn't need to think about, is my text the right size, is it the right color and that type of thing. And yeah, here we are at the end. I am doing the Ask a Speaker session after this, so if you have any questions, please come and talk to me. And yeah, thank you everyone for attending.